Well, thank you, Mike. Thank you, all the organizers, for having me here. It's a pleasure and an honor to have the opportunity to talk to you about our work on circuits of microfluidic memristors. And I added 2 words and a question mark to the title, because really, if anything, we made an infinitesimally small step at best in sort of computing with aqueous electrolytes. But I think it's a small step, and I hope you find this interesting. Before I say anything, I want to thank a number of postdoc, PhD students, master and bachelor students at my institute who contributed to this work, and I want to highlight Tim Kamsma, who has really been driving this work in the past 2-3 years on this. There's a collaboration with people at AMOF, Esther Alacon and Mark Aerts, that I'd like to acknowledge. We have a collaboration that I'll discuss at length with Jung Park and his research group in Korea. We never met in person, only online, but we published a paper here. And my local collaborators in Utrecht, Christian Spitoni from the Math Institute and Marjolein Dijkstra from the Dubai Institute for long-term collaborations. I have a few motivations to do this, and this work sort of started with a paper by Misha Bon and his collaborators entitled Liquid Flow Along a Solid Surface Reversibly Alters Interfacial Chemistry. This was 2014 or so about 10 years ago. And what they did is they could measure, I'm not going to discuss how they measure the surface charge of a water solid interface here, and if they start to, and they normalize that to 1, if they start the fluid to flow here, it drops by 30, 40, 50% or so, and if they stop the flow, it takes 20 minutes or so to recover here. That sort of experiment, I thought that's very intriguing and cool. Let's try and study this. And in the end, I'll show you Poisson-Planck-Stokes equation that we developed, but on top of that, a bit of chemistry in terms of dissociation and association constant, and surface conduction as an additional phenomenon. And then we could explain sort of this experiment. At least that's what we thought. And this took a few years. This is 2018 or so. Another piece of motivation comes from work by Liederik here, entitled Dramatic Pressure-Sensitive Ion Conduction in Conical Nanopores. And I'll discuss conical nanopores at length in this talk. But what they did is, you see here a conical nanopore. Here you see the length scale. So this is a micron-sized channel here. And what they do is they apply simultaneously a static pressure and the static voltage drop. And they measure, for instance, the current voltage relation here. This is non-ohmic. It has current rectification here. It's not a straight line. And moreover, they can tune this by pressures of the order of tens of millibars. So this is, in some sense, a pressure-gated transistor rather than so you can tune the conductivity by playing with the pressure rather than voltage-gated transistors that are in our electronic devices here. So that's also, that interested us to see how this works. It's a big motivation. And then there's a third motivation that's more a personal one, because I have always thought that I should be able, given my background as a researcher, to understand how batteries work, how hydrolyzers work, what a redox couple is, and stuff like this. But whenever I am in a seminar or whenever I read a text on electrochemistry, I get lost, and not after 10 or 20 minutes, but after 2 lines or so. This annoyed me, and that's sort of at some point I thought, okay, sit down and try to learn a bit of electrochemistry, and I want to share this with you. But that's a bit of a personal motivation. My starting point is the electric double layer within Poisson-Boltzmann theory in equilibrium here. And for this audience, I don't need to tell you any details, but consider a solid in contact with an aqueous, say 1,1 electrolyte for simplicity, and this solid has a certain surface charge, sigma, here, say a positive surface charge. Then the negative ions pile up. The positive ions don't like to be in the vicinity of the surface, so the bulk concentration here is only attained a few Debye lengths away from the interface, and the electrostatic potential goes from 0 in the bulk to a positive so-called zeta potential at the interface. Nothing new here, purely standard Poisson-Boltzmann theory. That's my starting point. I want to go to electric double layers out of equilibrium here, and for this we use the Poisson-Planck-Stokes equation, 19th century equations. Monica showed them yesterday already. Let me briefly discuss them also to explain my notation. Rho I is the concentration of species I, Ji is the flux of species I, and they satisfy a continuity equation. If there is no reactions, no chemical reaction, this is 0, but if there are reactions, then of course the species can disappear or appear here. Then there's a Nernst-Planck-Stokes equation for the flux that has 3 contributions. You recognize here the diffusion term here due to, this is essentially Fick's law. This is conduction, this is Ohm's law. If psi is the electrostatic potential, then minus the gradient of psi is the electric field. And this pushes plus particles in this direction and minus particles in the other direction by conduction. And if the whole fluid flows with the velocity u, then species I gets carried along. So this is straightforward physics. There's the Navier-Stokes equation, but we throw out Navier because we look at micron scale, so low Reynolds number flow. So there is dissipation, this dissipation due to the viscosity. You can drive the fluid by pressure drops. And very importantly here, there is an electric body force here. So if there is a space, somewhere in space, in net charge density, for instance in the electric double layer, and there is an electric field here, then there is a force acting on the fluid. And that also drives, that should be part of the force balance in this equation. So that's the electric body force, it's incompressible. And we have the Poisson equation of electrostatics, and we have the Gauss boundary condition with sigma, the surface charge here. So these are 19th century equations. Given a few other boundary conditions, this is a closed set that you can solve here. Special cases, just to get going, special cases, consider a neutral surface in contact with water here. Then you get a fluid flow and an electric current driven by a pressure and a voltage drop. This is only, it has only diagonal terms here. You get out the permeability of this system, and you get out the conductivity, Ohm's law, if you want, from this, where the conductivity is large if the mobility of the ions is large, and if the bulk concentration of the ions is large. If you have many charge carriers, the conductivity will be large. Yeah, so that's sort of built in. If you consider a charged cylinder, a charged surface, so the stern layer contains in this case a negative charge, and there is therefore a positive charge in the electric double layer here, and there's a zeta potential here, then you find that this 2x2 matrix actually also picks up off-diagonal terms here that are proportional to the zeta potential here. That's all comes out of this Poisson-Planck-Stokes equation here. And the physics is very simple, actually. Suppose you have such a situation and you drive a Pascal flow here, then this mobile charge here in the electric double layer gets carried along with the flow, and you get an electric current here. And if you apply an electric field here, then these plus charges experience this plus field, they get moved to the right, and they drag the fluid along, basically. So that's what the physics that goes in here. So this is electroosmosis, if you want. That's all built in. I'm not going to talk about it, but just to extend, this can be extended also to chemical potential difference of the salt. So consider seawater here and river water here. Then this matrix also contains, this is the 3x3 matrix in that case, the delta mu of the chemical potential picks up here. You get a salt flux here and the 3x3 matrix with elements that I'm not going to write down explicitly, but we have all calculated them. And this gives rise, for instance, if the G12 and the G13 and 23 give diffusiosmosis, so a chemical potential generates a fluid flow, and sort of it can also generate, a chemical potential can also generate an electric current, which can be used, for instance, in blue energy harvesting. But again, and you could make it a 4x4 matrix if you also change the temperature, for instance, left and right, and you get heat fluxes, etc. Yeah, so you can extend this, but I'm not going to build on that. Now, these Poisson-Planck-Stokes equations, we added a few things to them, and I'm just give you a few of, I call it our extensions. Of course, others have also done similar things here. One of the things is that the surface charge density can, of course, be fixed. You can say sigma is so many charges per square nanometer, and that's a fixed parameter, and you just do your calculation. But you can also calculate it self-consistently by using a bit of chemistry. For instance, if the charging is due to this deprotonation of the silanol group, for instance, you can define the fraction f of charged groups here. So f is then proportional to sigma, and you can write up a dynamic equation for this, a Langmuir type kinetic equation in terms of a dissociation and an association surface that couples actually to the proton concentration at the surface. So you couple this equation to the 3D Poisson-Planck-Stokes equation, and you try, you have to work a bit harder, but you can solve this also, for instance, and you take this into account. We've also done cases where this two-dimensional Stern layer, this quasi-two-dimensional Stern layer, actually can carry a surface current, so this charge is not fixed, but it can also move. We have done a bit of electrochemistry, actually. The Butler-Volmer equation can be used, for instance, to describe the electron transfer, the current that comes out or goes into a solid surface, depending on the redox potential and the applied potential, and I0 then is an input parameter that gives the exchange current, for instance, that gives all the quantum chemistry. In this case, that should give an I0, a prefactor here. So this is the Butler-Volmer equation. That also then couples, of course, to the 3D Poisson-Planck-Stokes equation. And then we go to cone-shaped channels, where I show you that if you apply an AC potential, it becomes a memristor that we can use. We think we made a baby step in the direction of neuromorphic computing. Let's see if you believe me after this talk. So this is the system of interest. We choose parameters very similar to this experiment that Liederik performed. So we have the Poisson-Planck-Stokes equation, and we have this model geometry here: a base radius RB, a tip radius RT, a fixed surface charge. Life is hard enough in this cone-shaped geometry, so we do simple sigma. We fix sigma to a typical potential here. Channel length L, and we apply a delta P and the delta potential here, and we solve these equations. What you can do is you can take linear combinations, or the electric linear combination and the salt linear combination, and you can calculate Q and I and J. And what you find is that Q and I, by the nature of it, always, because of this divergence-free condition and also the charge neutrality condition, they actually are not functions of the coordinate x that runs from 0 to L here along the channel. But this J of x is actually a function of x if you take a cross-sectional integration here. But in steady state, it must be a constant, of course. So what you can do is you can impose that this is in a steady state a constant, and this gives rise to a differential equation for the cross-sectional average salt concentration profile here. It's a bit complicated, but we can solve this differential equation, and what we get out is, and we can do this analytically, but let's look at the plot here. So this is the base, this is the tip, this is the coordinate that runs on the axis here, and this is the resulting salt concentration in units of twice the bulk concentration. So and what you see is that depending on the applied voltage, we find salt accumulation if the potential is negative for these parameter choices, and we find salt depletion in the channel if the voltage, the applied voltage is positive. And this is very similar to what we do what we find in full numerical calculations of this. This is depending a bit on the parameters, but it varies from very accurate to reasonably qualitatively okay here. And this effect depends on the Peclet number. The Peclet number is the dimensionless fluid flow, and it depends on the parameter we call delta rho that scales with RB minus RT. So this is really a phenomenon that is related to the cone shape. If in the cylindrical channel this is 0, and it depends on delta psi here. So you can imagine if there is salt accumulation, then the conductivity of the channel increases. If there's salt depletion, the conductivity of the channel decreases if this happens here. And if this effect is biggest if the Peclet number is 0, if there's no fluid flow. If there is net fluid flow, then this density profile of the salt gets washed out basically by the flow. But it's optimal if the pressure-induced flow is exactly compensated by the voltage-induced electroosmotic flow. Yeah, that's the physics here. So the key, and this is really the key to understand this talk, is ionic accumulation and depletion takes place depending on the polarity of the applied voltage, and it's optimal for zero flow conditions. That's the key physics that comes out of these Poisson-Planck-Stokes equation and of our analytic quasi-analytic theory here. Now, what we can do is for every delta P and delta psi calculate this concentration profile, calculate its average here, is indicated by the color plot here, and replace this in this 2x2 matrix, rather than have the bulk concentration here, have this average concentration here, which is a function of delta P and delta psi. So this looks like linear response, but it's not linear response because this element here depends on this quantity. And this quantity is largest on this line here, on this black line, where the Peclet number is 0, which takes place for the parameters of Liederik's experiments at voltage at 32 millibars per volt, tens of millibars of volt. That's the typical scale where this is optimal. So we sort of, this explains this small pressure, actually 32 millibar is small, is the dramatic pressure sensitivity that Liederik found in his paper. And we basically can describe the experiments of this. It's optimal if the optimal diodic behavior is found at Peclet 0. And for the remainder of the talk, I call this quantity G infinity here. The static conductivity, which is a function of delta P and delta psi here, that we have easily access to. Yeah? So that's... because what about if we apply now a time-dependent voltage, say an AC potential, having in mind that the diffusion of ions is slow. Ions diffuse micrometers per millisecond or so. So if you have a micron-sized channel, it takes a millisecond or so before the ions have gotten out or got in to this channel. And we found that this channel is actually a memristor, and memristors have been sort of predicted early on as the missing fourth circuit element next to the resistor, the capacitor, and the inductor here. And there's a beautiful theoretical argument you can ask me about this if you're interested in. How you recognize it if something is a memristor? Well, if it's pinched, if the IV characteristic is pinched in the origin and has an hysteresis loop like this, then it's a memristor. Yeah? And so what we did is we calculated, we apply this AC potential, we calculate through our finite element calculations, that's the blue curve here, we find this hysteresis loop indeed in the current voltage related. So and we have in mind, of course, that at positive voltages we have salt depletion. So initially, when there is still a lot of salt in there on the way up here, so the salt ions have not disappeared, the conductivity is high, but on the way back the voltage has been positive for a long time here, so the ions have disappeared here. But so if you go to negative voltages coming from positive voltages, the conductivity is still high initially, but by the time that you go back, the conductivity has increased again because of salt accumulation, so you get this hysteresis loop. So this is a memristor. We also have red curves here that are an analytic approximation that involve the G infinity, the static conductivity that we have easily access to numerically, and a timescale tau that is basically a diffusion timescale. This 12 is an analytic 12 that we found from our equation. So we have an equation of motion. We have Ohm's law, and the conductivity satisfy this equation. It basically says that the conductivity on the timescale tau relaxes towards its instantaneous static conductivity here, and this works out fine. And also the time dependence of this on L, this L squared dependence of the typical time scale is recovered. Of course, this all depends on the frequency of the applied voltage. If you do this too fast, then the ions can't flow, so then it's an ohmic resistor. If you do it too slowly, then of course there is plenty of time, and this loop closes here. But if this frequency corresponds to a period that is comparable to tau, here this time in intrinsic time scale, then you've got a maximum of the area of the hysteresis loop. So that's the thing. So the mechanism is really ions need time to enter or leave the channel. Yeah, that's the simple physics of this. Now what we did is we inspired by Hodgkin-Huxley theory for neurons that describe actually the sodium, potassium, and chloride channels, and a capacitive element mimic the cell membrane, we were inspired to consider such circuits here with 2 fast short channels and 1 long slow channel here. And this system is stimulated by a stimulus current I of t that we put in. So we have 3 equations for all these 3 memristors here, and we have Kirchhoff's law here that we solve when we solve numerically this simple ordinary differential coupled set of differential equations. And we do that in the case, for instance, of a current pulse here. So the current is 0, we pulse it, and it's 0 again. And actually we have 2 curves here, one just below threshold and one just above a certain threshold. And if you're above threshold, you find a full action potential. And if you're below threshold, and the difference here is 1% or so of this current, then we find a failed action potential. And perhaps you know that a neuron fires or it doesn't fire. It doesn't half fire, right? That's exactly what happens here. It's a very sharp transition between either firing if you're stimulated enough or not. If we consider a current step, so we go from 0 and then we step up, again, we have 2 curves here. If you're just above threshold here, then you find a train of spikes appearing. This is a a physiological phenomenon also. And if we add a 4th channel to this chain that is even slower, if you have yet another time scale in the system, then we find sort of a phenomenon called chattering here, which is also a phenomenological neural feature. So we find sort of neural behavior in this type of systems here. We have many more modes. Let me not discuss this. Now, so far we have only looked at electric double layers on the surface of the channel. Yeah. Now let's fill this channel with colloidal silica spheres to get volumetric electric double layers, which enhances the effects enormously, as actually was already discovered by our colleagues in Korea a few years ago. So they had a tapered microchannel built by soft lithography, here the length scale, so they're quite big, much bigger than before. And they fill this with colloidal spheres, 200 nanometers in size, and in an aqueous 10 millimolar KCl solution, the bio-length is 10 nanometers. And it's the channels, the fluidic nanochannels of between 1 and 50 nanometers that form the space in between the colloids where sort of the ions can flow. And this turns out to be a very strong memristor that mimics, in the case of AC potentials, a synapse, as we will argue here. So already in 2016, our Korean colleagues published this paper, and they redid the experiment for the present purposes, where they have, in the static case, a current voltage relation that is given by this blue curve here. It's not quite a diode, but still the potential at negative voltage, so the current at negative voltages is an order of magnitude smaller than at positive voltages. We adapted our theory a bit to account for these colloidal particles, and without fit parameter, it's not perfect, this red curve, but for our purposes it was good enough. We were happy with this to see that the static conductance we sort of understand experimentally and in theory. Now, they applied experimentally, and we applied in our theory the case where we apply an AC potential here, and you see the current voltage relation, which is a perfect memristor here, both experimentally and in the theory. We could also convince them to not only have 150 nanometer size channels, but also 50 and 100 nanometer size channels to check this time scale here. And indeed, tau is also in this case proportional to L squared. We don't have the 12D, the 12, I mean, it's a bit more complicated then, but we were very happy with this. So we think we understand this. Now, let's forget about static and AC potentials, but let's look at pulses. Pulses of voltages that we apply. So in green here you see 4 pulses, 4 positive pulses, and you see, and this is the experimental data, you see the current, the resulting current in blue, and you see that the current increases here upon applying a sequence of voltages here. And again, this is because ions flow in and flow in and flow in after pulse, so the conductivity increases and therefore the current increases. That's the physics. Yes? So if you have positive voltages, pulses, there is what's called in the neuro language facilitation. You get a stronger connection between synapses after a few pulses. And you can also have depression. That's why if you apply negative voltages here, the timing should be right here. If the second pulse comes a long time after the first one, then of course then the system has forgotten its memory here. So, and this really resembles like the behavior of synapses here. Now, you can apply 4 positive voltages, 4 negative voltages, but you can also, you have 16 combinations if you have 4 pulses at your disposal. So 16 combinations, all 16 are present, are listed here. And you can measure the conductivity after this 4th pulse, and you get 16 values in theory. And in the experiment, you find exactly the same ordering here. And the experiment was done after the theoretical prediction. You see a bit of uncertainty here. We have used this to do a little bit of reservoir computing here, where, for instance, this number 2 here is a 20-bit. It can be represented by 20 single bits, but also by only 5 4-bit strings here. So what you can do is train such a neural network to recognize that this is a 2 here by a smaller neural network than if you would use 20 bits here. So so you use a bit of the nonlinearity of a physical system to actually sort of separate an initial signal here. And we did this also with real handwritten data from a data set, and using the experimental uncertainty in our theoretical calculations, we find sort of 80% success rate in the confusion table here, which is very comparable to other techniques that people use to do to recognize these numbers. So this is an infinitesimal step towards iontronic information processes, and you can challenge me on this. But I think at least for me it's interesting how relevant this in the end is. Okay, to be seen. Now forget the colloids and go back to the conical channel filled only with an electrolyte, and let's have a look. Let's exploit the iontronic character rather than the solid state character of ordinary memristors here by coupling it to fluid flow and exploit chemistry, which is of course impossible in ordinary semiconductors. So suppose we are interested in 16 states by 4 bits. We could do that by 4 voltage pulses, as we did before, but you can also do it by only 2 voltage pulses simultaneously with 2 pressure pulses. So you can have 2 signals, and you can also have in 16 states altogether. You do the same thing, and you find after 2 of these pulses 16 different conductivities. So you have enhanced the bandwidth. You can have 2 signals simultaneously through this system, not only an electric signal, but also an acoustic signal here. So you can have twice the amount of information through the system, which is the bandwidth. A big disadvantage of all these memory effects is that they're very volatile. The memory is very volatile in the sense that the timescale after a timescale tau, which is milliseconds to seconds for these experimental systems, the system has forgotten its initial state. We want to make this a bit more non-volatile. And one of the ideas we have developed is by chemical substitution reactions with slow reaction rates. So we have the same channel here as before, with a 1,1 electrolyte, but also with trace amounts, micromolar amounts of divalent and trivalent ions we call B and A here. And we have receptors on the surface, and if a receptor catches a B, it's neutral, and if it catches an A, it's negative. Yeah, that's described by this reaction. We have this Langmuir equation to calculate this surface charge self-consistently, where we have a reaction constant, equilibrium constant K, and a rate here that we can set. And now we do the following procedure. we do the following procedure. We have this channel and we let it equilibrate first. No voltage, no nothing applied. So there is a certain surface charge on this surface out here that we normalize to unity here. Then we switch on the voltage to 1.2 volts here. Ions get sucked in, and it takes a millisecond or so for these channels. So ions get sucked in. We perturb this balance here because the concentration of A and B are in here, such that the surface charge actually goes up. I'll finish soon. The surface charge goes up during, in this case, half a second here. The surface charge goes up. Then we switch off the voltage again. Within a milliseconds, these ions are out, but these ions are needed actually to restore equilibrium. And they're not there or at much lower concentration, so relaxing back to equilibrium takes ages, 1,000 times longer actually. This curve does decay to zero, but on a time scale of 20 or 30 minutes or so. So what you see here is accumulation, which if you plot the conductivity of the channel here, you find short-term potentiation due to the accumulation and of the ions that takes place on the millisecond timescale, which is a very sharp rise here. And surface conductions is long-term potentiation here. It takes ages before this system has relaxed to equilibrium again. So the memory has a much longer timescale here due to slow chemistry. So there's chemical regulation. We also have a logic AND gate by applying a concentration pulse and a voltage pulse together. We have had a very strong effect only to the conductivity or to the surface charge in this case if you have both a chemical and an electric pulse. If you have only one of them or zero, we find a tiny effect. So this is a logic AND gate, but a chemical electro AND gate. And this is very similar to NMDA receptors that are associated with Hebbian learning. Do I have any authority to tell something about NMDA receptors? Absolutely not. I know nothing about this. But I happen to have supervised a PhD student, a master student in theoretical physics. So he graduated with me, did a project with me. But he also has a master degree in neurosciences. Coincidence. And this guy sort of guided us into the literature, so I read sort of the 1,000 papers that are out there on NMDA, I read the 2 or 3 that he told me I should read. Yeah, so I don't have too much knowledge about this, but this is very similar to so-called NMDA receptors that we all have in our bodies. If time permits, which is not, let me skip a few of these things and conclude. I hope to have shown you that the Poisson-Marx-Stokes equations for aqueous electrolytes can be coupled to Langmuir surface kinetics, to conducting Stern layers, to Butler-Volmer equations, to model iontronics here. Fluid flow affects interfacial chemistry and causes heterogeneities. I did not discuss that in any detail. Conical channels are pressure-gated transistors, and the physics is really due to non-trivial salt concentration profiles. Salt gets sucked in or squeezed out of these channels. This nonlinearity gives rise to action potentials and spike trains if you do small circuits. If you add charged colloids and add the number of electric double layers, this effect gets enormously enhanced, and you can use chemical substitution reactions to reduce the volatility by slow charging reaction. And we have some extensions, but let's stop here, and thank you very much for your kind attention.
Thanks a lot, René. Question, Paddy? It's a lovely talk, René. I have 2 questions, and I'll be quick. The silicon particles, are they moving?
No, they're stuck. They're fixed. I mean, this research group in Korea are in mechanical engineering. The colloids couldn't care them less, right? I mean, I'm a colloids guy by background, so I care about the colloids. I think what happened, they squashed them through their electric double layers into van der Waals attractions, and it's one clump of material. They call it a crystal. I think it's more a glassy thing, but it's a very dense, so they're not mobile. Yeah. we haven't done this yet. It's been on my mind, but here we focus on aqueous system also because we have several ongoing other follow-up experiments, so we focus on aqueous systems. But yeah, I have this, well, as we collaborated on in the past, right? These oily solvents, yeah, they could also be very interesting, but I have nothing to say about that. We don't have any results. We can discuss in private, perhaps, what. Yeah. The valent, for these, so we focused on 1-1. Electrolytes, generically, just Amphos-Boltzmann theory and for Planck-Stokes theory are supposed to be sort of okay. Much better than if you go to divalent or trivalent ions. But for the reactive ions that are called A and B in this, when there's chemical substitution, this also works for monovalent ions, but less. It worked much better for divalent and trivalent ions. And if you go to higher valencies, it works even better. But the theory gets less and less reliable to do this. So we thought 2 and 3, divalent and trivalent, yeah, was sort of our compromise, and it's still halfway okay. No. But I take a big interest actually in adapting the channel shape. Actually, the shape of the channel is fixed, but wouldn't it be nice if you have a sort of a coating of polyelectrolyte, for instance, that can swell or deswell depending on, and then the shape of the channel changes. Okay, we are thinking along these lines, 0 results as of yet. I rely on master students here and whether or not they show up and how good they are, and so it's yeah.
So I don't understand how
Okay. The Debye length is dictated by the salt concentration far away from the interface, right? And that we can tune by applying a voltage. If you have a negative voltage in the channel, then ions get sucked in, and a positive voltage, ions get squeezed out, basically. So that changes the salt that changes the Debye length. But I'm not sure if I answered. Yeah. Okay. No. Okay, no. We changed the surface charge. This because. Yeah, okay, yes, the surface charge, it changes the double layer, but not necessarily the asymptotic, the Debye length. Yes. Yeah, we calculate the surface charge as a function of the position. So at the inlet of the channel, it's different from the outlet of the channel, but and then we average this to get the conductivity out. But we no, we calculate sigma as a function of position and time, and then it depends. Sometimes it's fast, and sometimes it's slow. And the charging up is very fast because the ion concentration is large, and then we take out the ions by switching off the voltage, and then it takes ages to relax to equilibrium. That's how we increase the non-volatility of these channels. Okay.
Last question from Ludwig. Potential which is required by the colloid.
Yes, very much. Yes. Yeah, there are many colloidal particles and therefore many electric double layers, and this gives rise to a much stronger effect than only charge on the surface. So yes, the Donen potential is key here, as is also actually the case in In a normal case, yes. Yes, no, that's true, yeah.
Okay, we should move on. Thanks very much again, René.
Thanks.